Hello everyone, and thank you for attending this presentation on recommendation systems. So what are recommendation systems? To put it very simply, a recommendation system is a tool or a set of tools that are used to recommend a product to a customer. This set of tools tries to identify what the customer would like to purchase and recommends exactly that to increase the customer's probability of purchasing the product or service. So, why do we need a recommendation system that recommends products or services to customers? This is because customers often don't know what they want or even what is available. With companies constantly bringing out new products or new varieties of the same product, there are just too many choices available to the customer. And the sheer volume of products and services that the customer has to choose from makes it really difficult for them to make a decision on what to purchase. Recommendation systems, however, can be trained to mine through vast amounts of data on customers' past behavior and characteristics and predict their interest and drive customers to exactly the product that interests them. And they can even help customers discover products or services that they may not have found on their own. So they're extremely useful. And how does the recommendation system come up with recommendations? Well, recommendations can be based on various criteria, such as the customer's own past purchases, the customer's past behavior, such as search history, web visits, etc., characteristics of the products that they have purchased in the past, their demographics, as well as behavior of other customers who may be linked to this customer in some way, either through some same or similar product purchases, or similar behavior, or similar demographics. And together, all of these techniques can be used to form a comprehensive toolkit for building robust recommendation engines. One method for generating recommendations is the item-item similarity model. In this approach, we try to identify products that are frequently purchased together. So, an item purchased by a user is used to find for him other items that may have been most commonly purchased along with this item by other people. So the first step is to identify the user's purchases. So we extract all the items that this user has previously purchased from their transaction history. In the second step, we try to compute similarity scores between the purchased items and all other products in the catalog which the user has not yet purchased. And a lot of different similarity measures can be used, but cosine similarity is most commonly used. Next, we combine the similarity values across multiple purchased items to identify strong patterns for the unpurchased items. Next, we rank the unpurchased items. Basically, we sort products by their combined similarity scores to identify the best matches. And lastly, we generate recommendations by creating the final recommendation list from the highest scoring items from the list of unpurchased products. Some of the advantages of this item-item similarity method are: one is that it discovers new items based on collective purchase behavior. This means that it can expand the user's interest based on what others have purchased. Secondly, it is not limited to similar features, so it finds relationships through actual purchase patterns of other users. While the item-item similarity method is a popular technique used in recommendation systems, it faces several challenges. The first challenge is the cold start problem, which means that this method is difficult to apply to new items or new users due to insufficient interaction data. When a new user joins, for instance, there may be insufficient data about their preferences, making it hard to generate recommendations. Similarly, new items may not have enough ratings or interactions to be effectively recommended. The other problem is the issue of sparsity. User item interaction matrices are often sparse, meaning that most users have rated only a small fraction of items. This sparsity can make it very difficult to find similar users or items. Lastly, there is the problem of scalability. As the number of users and items increases, the computation required for this item-item similarity method can grow significantly, leading to scalability issues. Another method of recommending products to customers is based on what is called the content-based recommendation system. In this model, item features are used to provide recommendations for similar items. An example would be movies, where the genre of a movie that the user has watched in the past can be used to understand what type of movies the user likes, and similar movies or similar movies belonging to the same genre can be recommended to them. However, genre is just one feature of a movie, and usually a movie contains several other features such as the main actor, the director, the producer, etc. And sometimes the individual's preferences may be linked more to one of the other features. For instance, maybe the individual really likes the director of this movie and would be interested in watching other movies by the same director. And therefore, we would want to recommend those movies to them as well. Just like a movie contains multiple features, similarly, most product contains many features, and it is a combination of these features that we must consider when deciding what product to recommend to the customer. The first step in implementing this method is to extract features from the items. This could include product descriptions, product attributes, or any metadata we have about this product. And then we combine all of this information. Next, we convert these textual features to numerical embeddings. This can be done in many ways. One approach is to use a pre-trained language model, such as the BERT model, and extract its embeddings. One can also use the term frequency inverse document frequency measure. This measure, called TF-IDF in short, is a statistical metric that evaluates how important a word is to a specific document within a collection of documents by increasing the weight for words that appear frequently in that document but rarely across the entire collection. Once we have the numerical embedding vector for each product, we can calculate the similarity between the different products. Lastly, we can rank the unpurchased products by their similarity to already purchased products to generate recommendations. One thing to note is that content-based filtering methods excel when user behavior data is limited. And in those cases, it relies instead on rich product information to find meaningful connections. Just like all other recommendation systems, the content-based recommendation method also has some advantages and disadvantages. One advantage of this method is that it can capture the specific interest of the user and recommend even niche items that other users may not even be interested in. Another advantage is that it can be used when new items are introduced as long as we know the feature of the new item. So it does not suffer from the cold start problem when it comes to new products. This method also has some disadvantages. One disadvantage is that the model is limited in its ability to expand on the user's interest and can only recommend items the user is already interested in. The second disadvantage is that the cold start problem still exists for new users. The model does not work for new users as we do not have any information on their interests. Another method for generating recommendations is using the LightFM recommendation model. In this method, we assume that an item is represented by a vector of numbers. However, we assume that these numbers are hidden or unobservable to us. These types of vectors, whose elements are unobservable, are also called latent vectors. In fact, LightFM goes a step further and also assumes that each user can be represented by a latent vector. Usually, the problem is set up in such a way so that one vector is a row vector and the other vector is a column vector of the same dimension. So the user vector may be a row vector, for instance, and the item vector may be a column vector of the same dimension. Since the two vectors have the same dimension, this means that the dot product of the two vectors is just a number. And the assumption is that this number represents the rating of this user for this particular item. So we go ahead and compute the dot products for every item user combination. Now note that most users purchase only a fraction of all the items. So when we look at the user item rating matrix for all possible users and items, it is actually very sparse. However, in this case, since we are using latent vectors to represent these items and users, we will not have a sparse matrix. Each cell in this matrix will actually have a number, even if it is a very, very tiny number. So, assuming latent vectors for both users and items allows us to convert the sparse rating matrix into a dense one, which means that it has fewer blank cells. So we start by assuming some initial values for the latent factor embeddings to obtain this dense rating matrix. And then we use the learning to rank method. And what is that method? We basically start by picking a user, a positive item, and a negative item. A positive item is an item that the user has purchased. A negative item is an item that the user has not purchased. The assumption is that in the dense matrix, the rating for the positive item must be higher than the rating for the negative item. If not, we change the latent factor embeddings to increase the rating of the positive item and decrease the rating of the negative item. And we continue to pick other negative items in this manner until the rankings between all item user pairs are correct. So that is how the LightFM model works. The LightFM model also has some advantages and disadvantages. One advantage is that it is a mixture of item-item filtering and content-based methods. So both user behavior as well as item and user features can be incorporated into the same model. Secondly, since it uses latent factors, it can handle cold start better than other methods. This is because LightFM also learns embeddings for individual user and item features. For example, it learns the embeddings for maybe the user age, the user gender, maybe the item category, the item genre, etc. So when a new item is introduced, it lacks interaction data. However, LightFM can still generate recommendations by summing the embeddings of its known features. For example, the feature, its genre or its description keywords, and by summing these embeddings, it can create an item embedding. Similarly, for a new user with no past interactions, LightFM can construct a user embedding by summing the embeddings of their available features. For example, demographic features or stated preferences, etc. LightFM method also has some disadvantages. One disadvantage is that in practice, when adding item features or user features, the model performance may decline. Secondly, the method needs a lot of computation and careful feature engineering and is more complex than other methods like item-item similarity or content-based recommendations. Next, I will hand it over to Krishna and he will go through some of the other recommendation methods.
Let me talk to you about trigger strategies, which are used basically to identify and leverage joint purchase patterns. So how it works is we identify products which are purchased together in short frequency of each other, and we call them joint purchases. And then we calculate the joint purchase rate between products A and B. So say if the two products are A and B, joint purchase rate AB is basically times A's purchase being in the denominator, and times A and B are purchased together is in the numerator. So if this joint purchase rate is high, then we would recommend product B whenever product A is purchased. Similarly, we can calculate joint purchase rate B2A, and if that is high, then whenever B is purchased, we would recommend A. And what are some of the advantages of a system like this? First thing is exceptionally high response rate, because if the trigger is applied correctly and the right timing, because these products are purchased with very high frequency together, you get a very high response rate. It helps us get a good understanding of what are the complementary products, and it's very intuitive and easy to explain. uh, Disadvantages, there might be limited applicability. It cannot be your main product recommendation system. It supplements and complements the other system by adding an additional layer. Uh, and then uh, it requires significant history and a lot of data, because there might be a lot of spurious joint purchases triggered by other events. So you need a big longitude of data as well as a good cross section to make sure that you are actually picking up true patterns. Let us next discuss popularity models. So popularity models are best described as a baseline approach which leverages the popularity of certain products to make recommendations, and so it is very useful when there is not enough history, either due to the cold start scenarios, or when you are dealing with new users with limited purchase history. So with the cold start challenge, the issue is that there is no purchase history available for the users. And the solution is, if you have a system of popularity based models, then you can use that to make recommendations. And then one thing you have to be careful about this is that popularity is a very fickle metric. It can vary a lot in short term depending on short term trends and what's going on. And if you use that to make predictions, your rather if you use that to make your recommendations, then your system will not be as stable, and the recommendations will not lead to good purchases. So you have to average out the product ranks over some time period to identify products which are truly popular, to take care of short-term trends. At the same time, you cannot go too much back in history and take irrelevant products. So this balance has to be done to get up with the right popularity model. And so the final output, of course, will be to generate this recommendation. And the benefit of this is it is very lightweight to implement, and works across a lot of situations where it would not be possible to generate recommendations. And to summarize key advantages, as we have discussed: zero dependency on user history, solves the cold start problem, works immediately for new users, and simple to implement and explain. And the drawbacks are, there isn't really any personalization here. You are just using product sales trends to make recommendations. So obviously, when you have richer data and you can use that personalization, you will get much superior results. Mm, and uh, it a continuation of that thought, it basically will miss niche preferences, goes back to lack of personalization, basically. Let me now take you through a case study where we implemented product recommendations for digital subscribers of a leading health magazine. So our product recommendation framework, which we developed, leveraged the different types of models we have discussed, from popularity models to trigger models to content based models. So we broke the population down into different pockets. For existing products which had already been available for some time, and for existing customers, uh, the we used uh, user-based recommendation models. We use content-based recommendation models, uh, popularity-based recommendation model, and layered a trigger strategy on top of it to create uh, this entire recommendation regime. This was the most sophisticated group. Why we needed something like popularity here as well, even though it's a baseline model? Because not all users have enough history. So for newer users, this was a good way to generate recommendations for them. Then for new products and existing customers, so that's always a challenge, right? That new products are being introduced and being offered to the customers. uh, so we used content-based models because those look at product similarities in making the recommendation, so they were the most appropriate for this. And then for existing products, new customers, so these would be people with no history, we use popularity based models to make our recommendation. A good validation approach was needed to make sure what we built was actually holding true when applied to real data. So what we did is we introduced a rigorous approach which involved backtesting. How we did it was we used data up to 2022 uh, to build the model, and then for early 2023 we looked at purchase performance, and we scored the model built with data up to 2022 to generate recommendations. And these recommendations were then backtested with the actual purchases. And so we divided the cohort into two groups, one which received the recommendations from the model, and the other group which did not receive the recommendations. While this we were backtesting, we could identify the people who received recommendation which would match what the model would recommend for them, and that was kind of our test group. And the control group would be those who received recommendations which were different from what the model would recommend. uh, and the performance metric was purchase rates. So uh, let us first discuss the results we obtained for existing customer and existing products. Uh, and in general, we saw big improvement when we applied the model. So uh, for subscriber who had purchased in the past year, uh, in this case that would mean in 2022, we saw a model lift of 37.5% because the purchase rate improved from 0.24% to 0.33%. And for subscribers who purchased the product a little earlier, say in 2020 or 2021, and did not purchase anything in the last year, we saw the purchase rate improve from 0.16% to 0.23%, which meant a model lift of 43.7%. For new products, the recommendation model did an even better job. So, uh, if you looked at the group which received recommendations for the new model but were not part of the model list, uh, the response rate or the purchase rate was 0.15%. But if you looked at the group which made the model list, uh, the purchase rate was 0.63%. So that's a 420% increase in the purchase rate. For new customers too, the recommendation system, which used the popularity based model to make the recommendations, led to a good improvement in their purchase rate. The group which was not part of the model list had a purchase rate of 0.14%, whereas the group which received model recommendations had a purchase rate of 0.19%, a 35% improvement in model lift. Now, uh, uh, so we have seen that across all the groups, the model did a very good job. In some cases, it was very, very strongly pronounced improvement. In other places, there were still very good improvements. So clearly, the recommendation system, if done properly, can lead to significant improvement in purchase rates. Thank you so much for taking the time to attend this webinar. I hope you found the content to be of use to you. We look forward to seeing you again at our next event.